Okay, so today we will finish up with the recursion chapter. Then we will go back to separate compilation and namespaces. Any questions from yesterday's class about recursion? Okay, let me find that chapter again. Recursion, it's here. Okay, so the last time we were talking about tail recursion. Okay, tail recursion is a special type of recursion. It's a recursion. And what's the definition of recursion? Recursion is if a function calls itself, it's a recursive function, either directly or indirectly. Remember mutual recursion, the function may call itself indirectly. F calls G, G calls F. This is still recursion. So tail recursion is a special kind of recursion. It says that if the last thing a function does is another recursion call, then it's a tail recursion, like this one. Okay, let's say I am writing str length. Okay, str length takes a constant character array, and remember this was the simplest way we can write it. But let's say we are not writing it that way. We are gonna call another function strlen2. strlen2 takes the string, the character pointer, and an index, and it says that if I am pointing to a null character, I will return just I. Okay. Otherwise, I will return s plus 1, I plus 1. Okay. So this is a tail recursive function. It's a tail recursion, and it's called tail recursive function. The definition of tail recursion is exactly this: a function that is tail recursive if it has the property that no further computation occurs after the recursive call. Okay. So in this case, this is tail recursive because the last thing before the return this function does is making this recursive function call. Okay, this is called the tail recursion. The ones that we have written previously, what did we write previously? Let me show you this power thing. Maybe I can, yeah. So this one. The last thing that this one does, it returns the power of x to the minus 1, but the last thing that it does is it calls this one and it multiplies it with this x. So this is not tail recursive. So last thing this function does is a multiplication operation, right? It is not a recursive function call. Again, if we have written any other functions that we have written before, yeah, this one again. The last thing this one does is, other than the base case, of course, writing out the string on the screen. So it is not a recursive function call. And maybe we can do it this way too, right? The last thing that this function does, what is this? This string length, right? What is the last thing that this function does before returning? It is the last thing that this function does before returning is, is this addition, right? It is not this call. Okay, it is not this call. So this is not tail recursive. So let's go back to definition of the tail recursion again. Okay. So that's the definition of tail recursion, and this is a tail recursive function. As you see, it is the last thing that this function does. So why are we interested in this property? Any guesses? This is very important actually. Why? Why is this so important? The last thing that a recursive function does is another recursive call. Remember the picture that I showed you at the beginning of the chapter, this one? Obviously, this is not a recursive function, tail recursive function. Why? Because the last thing is, what is the last thing that this function does? Is the assignment operator, right? Multiplication and the assignment operator. The recursive call is recursive call comes way back before that. Okay. So let's imagine what happens. Let's imagine what happens when I make this recursive call. I get a new value, okay, and I multiplied it, and I signed it, and I returned it. So all the data that I need is in my stack, right? T1, T2, everything K is there, and I use them up, okay? Because after the recursive function call, I need to make all of those calculations. But if the last thing is a recursive function call, I don't need to keep anything in my stack because I am not going to use them anyway, right? After the function returns, I am not going to use my stack variables. I am not going to make any calculations on the local variables. So before I make the function call, recursive function call, I may get rid of everything that I reserved on my stack. Okay? So that means that every function call, every time I make a function call, is like a loop iteration. I am not taking any space from my stack, and I'm ignoring everything that I have allocated so far because I don't need them anymore. So that's why we say that tail recursion is a very efficient way of writing recursive functions, okay? And they can be easily converted to more efficient iterative solutions, even by the compiler, okay? When the compiler realizes that you have written a smart compiler, of course, when the compiler realizes that you have written a tail recursive function, then the compiler will automatically convert it to a iterative solution, and that way you won't have any problems with the buffer overflows or the stack overflows, etc. Okay, so it is as efficient as iteration, and it is as beautiful as recursion. Okay, so best of both worlds. So try to write these kind of tail recursive functions. Okay, but see, this is very different than what we have written before. I need to send this variable to the functions all the time. Yeah, I know that. So I need to think a little bit differently, but it can be done. If you think a little bit about it, it can be done. It's not that difficult. Okay, good. So two important things. What is the tail recursion and why it is important? You need to know these. Okay, any questions? Good. Can we write the factorial in a tail recursion fashion? Write the factorial. The last line in the factorial is n times f n minus 1, right? So that's not good. How would you write the factorial? Let's write the factorial.
We can create another function that takes the accumulation as a parameter.
Yeah, exactly whatever we did here. So maybe we should do this. It is factorial tail recursive factorial, ft, factorial tail recursive. It will take the integer to take the factorial, and maybe I should get the multiplication of the number so far. So what do I do here? I will say it is m, and I will call, this is the real factorial. It takes an integer I, and it says that I will return f t I comma 1. Okay? And what would be my base case? My base case would be if I is less than or equal to 2, less than 2. If I is less than 2, just return m, right? Is that correct? Yeah, just return m. For 0 and 1, it's going to be 1. And then what? And then what? Return So since this is going to be tail recursive, I have to do this, ft, right? ft, then what? I minus 1 time, comma, m times what? I, okay. See, it's very similar to writing an iterative loop actually. But it is, I have the base case, okay. Now I have the recursive call. And inside, before doing the recursive call, I do this separation into two, right? Make I smaller and do the solve the easier problem. Okay. So before calling that function, recursive function, you do it this way. So this is as efficient as writing an iterative function. Try it. Okay. Write. Okay. Exercise for you. Write the factorial. Okay. Write the factorial or the addition, whatever, from 1 to m, using straightforward recursion, and test it with a very large number, okay, very large number. In a few seconds, you will see that you will get a buffer overflow error, okay? But if you write it in a recursive way and use the optimization flag with your compiler, minus O3 optimization flag, okay? In that case, you will see that your function goes on. It doesn't stop. Of course, the number you are going to get will not be meaningful because you will have double overflows, right? Your number will be so big it won't fit into integers or doubles. Yeah, that's true, but at least you won't get any stack overflow errors. Okay, just try it, and you will see that tail recursive functions are as efficient as iterative functions. Okay, good. Any questions? I need a question. Oh, I forgot my. Just put the header, the title of the course and the date. Any questions? Yes.
Is the compiler smart enough to know if the recursion is tail recursion or not? So if it have any operation after the return, it will automatically save all the variables in case we will need them later on.
But that's what I said. I mean, this conversion can be done automatically by the compiler. How you mean that if the function is not tail recursive, the compiler is smart enough to make that conversion to tail recursive version.
So if it's tail recursive, you said that it will not hold any.
Yeah, it will make that optimization. Yes.
Yeah. So if it's not tail recursive,
yeah,
it will automatically know it's not tail recursive and will keep all the variables, right?
Well, I mean, if you need them, but yeah, what you are saying is, by mistake, I have written a function which could have been a tail recursive function, but I have written it in not tail recursive. But it could have been tail recursive because after the function call, I am not doing anything. So yeah, sure, the compilers are smart enough to do that. Yes.
So it will know it's a tail recursive function and will get rid of the.
Well, by combining with other types of optimizations, if you declare a local variable in a function, and if you don't use it, compilers are smart enough to ignore that local variable. Okay, they don't serve. So if you are not using a local variable after you have calculated something, they are smart enough to not make that calculation. Okay, so if you are done with a local variable and if you are not using it, it will ignore it. So that will lead to converting your function to a tail recursive function. But it depends on the compiler. Okay, compilers and processors are usually designed together. Okay, that's where this idea of RISC comes from. Reduced instruction set computers, RISC. Okay, their instructions are not very, but their instructions are limited. But these kind of processors are designed with the compilers and the software. Okay, So they know each other very well. So compilers has to be very, very smart to make those kind of optimizations so that they can take advantage of these kind of processors.
Is x86 RISC is 86 architecture is a RISC or CISC architecture?
Well, initially it started as, I mean, RISC appeared much later than the Intel architecture, but the recent iterations of Intel architecture definitely uses RISC ideas. I cannot say it's a RISC processor.
x86, the Intel architecture contains really complicated instructions.
Yeah.
Really wonderful.
Yeah, I cannot say they are RISC processors. Nowadays, we don't have any RISC processors anyway. It has changed. Nowadays, the processors use all kind of ideas, and some of the ideas come from this technology. Okay. Some people say that these are not processors; these are computers. Actually, I mean, we don't know exactly what is going on with the processor. They say that there is an operating system running on the processor itself. So we communicate with the processor using that operating system. So there is a whole bunch of software running on the chip itself in a very, very fast way. Okay, so I talked about mutual recursion, and we looked at this example again. So this is unnecessarily complex, unnecessarily complicated example, but it works. So the idea is, if I like to calculate the even number of ones, let's say this is my string. Let's count the number of ones. 1, 2, 3. There are 3 ones, so there are odd number of ones in it. So the idea is this. I would take the first one, okay? If I am trying to find if it's an even numbered ones, if the first one is 0, then I would say that if I call odd number of ones on this part, if it comes with true, then I would say that this is not an odd number. If it comes back false, then I would say this is even number. Okay, that's the idea. Okay, so if this is 1, and I am this function, even number of ones. If this is 1, and if this is odd number of ones, then I would say true. Yeah, I have an even number of ones. That's what we are doing. If string length is 0, then I would say it's okay. 0 means that it is 0. It is even number. So I just return true. Odd number say that if the length is 0, then it is not even. It is not odd. It is even. So I would return false. Okay. If S0 is 1, what do I do? If this is 1, and if this part contains odd number of ones, and I have 1 here, that means that I will add them both, and it's an even. So that's what I do. If this one returns 1, then I will true, and I will return true. Otherwise, I will. If this is not 1, then I will return this one. So that's what these two functions do. It's just an example to show how the things work. Okay, so I don't know what. Yeah, I think this is a straightforward version of it. Yes, it takes a constant character. If my current character is a null character, then I said return true. Then I have a result even n s plus 1. If this one returns true, okay, if this one returns true, and if the current character is 1, no, if this one returns false, and if this is on 1, then I would say it's an even number. Otherwise, it's an odd number. So you don't need to write mutual recursive functions to solve this case. It's an exaggeration. I don't like it, but the idea is there, right? Remember what example I gave you? That minimax example? Minimax algorithm. It uses exactly the same idea. minimax algorithm that is used for the chess playing. Let me try to, am I connected? So look at this one, minimax algorithm and maybe some images. I think this is good enough, yeah. Where is the, yeah. This is max and min, 2 players. Max is white side, min is the black side in chess, okay, or any other game. So at the end, if it's a plus thing, the max wins. If it's a negative thing, min wins, okay. At this position, max says that I am trying to maximize my gain. At this position, min says that I am trying to maximize my gain. So at the end, it turns out that I am maximizing here and minimizing here. Maximize, minimize. So this one calls these two calls these four. These four calls these, okay. So this one calls this one calls that one, and it goes that way. Okay, so there are really good algorithms that does mutual recursion, but this is not a good example, unnecessary example. Okay, good. Any questions? Okay, if no question, then I will continue. Binary search. So the binary search is a very classical example of doing recursive calls. Binary search says that if you have a sorted array like this, yes, it is sorted 1, 7, 9, and 57 at the end. I can make a search on this one in a very, very efficient way. How? I would do this. Give me a number. Let's say your number is 31. I would compare 31 with the middle element. If this one is 31, then I would say that I found it. Otherwise, I would say that I don't need to look at this part anymore. Okay, I don't need to look at this part anymore. Why? Because 31 is greater than 10, and this array is sorted. 31 cannot be here. So I will look at this part now. So the problem is exactly the same problem. So that's the recursive case. The problem is exactly the same problem, but the size of the problem is just a half, right? So I decrease the size by 2. I saved lots of time, and the problem is exactly the same problem as before. So this is a typical recursive environment. So I would compare in the middle element 31 with this one, 27. It's not equal, but I know that 31 is larger than 27. So I would ignore this part, and I will check now this part. Okay, in the middle I compared with 31, and 31 is equal to 31, and I said that I found it. If I were looking for 32, then I couldn't find 32, whatever I do. At the end, I would say that, okay, these two I am looking at, and in the middle there is nothing, so none of them is 31, 32. Then I would say that I couldn't find it. So I am dividing my array into 2 until I find my number or until I don't have anything. I cannot divide it. Okay. So that means that if I have an array of 1024 elements, in the first iteration, in the first recursive call, I would get rid of 12 of them, then this much, then this much, then 64. You got the idea, right? How many times do I divide this array at most? I divide this array at most log to the base, okay, log, okay, base logarithm of 1024 to the base 2, and it is 10, right? Okay, so that's as efficient as this much. I mean, I have 1,000 numbers in my hand. Okay, I am doing this recursion 10 times. I am looking at 10 numbers. It gets even better. It gets even better if you have 1 terabyte of data, which is 10 is kilobyte, 20 is megabyte, 30 is gigabyte, and 40 is terabyte. If you have 1 terabyte of data, 1 terabyte of integers, sorted integers, it takes you only 40 recursive calls to find your number, right? 1 terabyte is a very big, very large number. It's a very, very large number, right? It is 2 to the 4. 2 to the 4 is too big. Okay, so this is very, very efficient. Very, very efficient. We like this kind of search. Of course, what is the precondition? Precondition is the array has to be sorted. Sorting is not cheap. Sorting is not cheap, right? I mean, but if you have a sorted array anyway, in that case you could use the binary search. So let's see the code from the book. Directly code from the book. I will get this one. Yeah. My recursive function will be this search. It will take a constant integer array. It will take the first and last index inside the array where I am going to make the search, and I will of course need the key. I am looking for this key. If I find the key, I will set this to true. It's a call by reference C, and I will set the location to wherever I find it. Okay. Here's an example of how I use it. Array size, whatever array size is, I don't know, 10. Okay. And I fill the array with these numbers. So the numbers will be 0, 0, 3, 6, 9, 12, etc. These are the numbers. Okay, and I print out the numbers. Okay, so I have 10 numbers in my array. Those are the multiples of 3. And I have the key and location. These are my local variables. And I ask the user, give me a key number. I will look for it. And I will say that, okay, you gave me the key. Key is here. Inside this array A, I will look for the key between these two index positions, 0 to final index. And if the result is found, then the found will be true. If it is true, then location is the valid location. If the result is not found, then I will say that I couldn't find it. Okay, so this is how you use it. And then what? And then let's look at this. Let's look at the implementation of the function. Okay, this is the base case. This is the base case. If first is greater than last, that means that I used up all of my elements. I cannot find anything, right? If first is greater than last, then I will say I found this false, and I just return. Since this doesn't return any values, I set found false, and I just return. Otherwise, if first is not greater than last, otherwise what would I do? I would do this. I would take the mid position of the array, and I will check if the mid position array is the same as key. If it is there, okay, if these two are equal, then found is true and location is mid, and I return. Else, if I couldn't find it, now I have to make a decision. Should I call my recursion on the first part of the array or the second part of the array? Okay, so this is the base case. This is another base case. These are the two base cases. And how many recursive calls I am making at each from this function? How many recursive calls I am making from this function? Just one, right? Either this or that. I am not doing both of them at the same time, right? Either this or that. Okay? So base case, then I am going to make a decision. My result is either in the first part of the array or the second part of the array. If it is in the first part of the array, how do I know that? If the key is less than the middle element, then I will look for between the first and middle minus 1. Okay, everything is the same. If it is in the second part, then from middle plus 1 to the last. Okay. Good. Since this is a void function, I did not use any return statements. This is not a good idea actually. I think I would have done this with a. Let's fix this. Okay, this is integer now, and I get rid of C. Much better. Okay, so what do I do now? You understand what I'm going to do, right? If I find the result, I will return the index. Otherwise, I will return a -1. Okay, so let's fix this. So first is greater than last. I should what? Return -1. Okay. How about this one? If key is a mid, then I would return what? Return the mid element. Okay. If key is less than this, okay, I'm getting rid of these. Okay. So how should I change these? If this what? Not, no, you cannot say nothing. You have to return something. Just type return here, right? And return there. Okay, good. Much better. Why? Because this is more readable. I don't have to. Because I mean, void functions. I don't like void functions. I mean, function should return something. I am calling it and returning something, and it's meaningful too. It's -1. It's error. Okay. So I don't need to keep to found and position, etc. Question: is this a tail recursive function? Why? It's louder. Say it louder, so that everybody can hear.
Because it has a condition, so it's not doing it either returns if the key is less than a mid or if it's greater. So it doesn't do both of them. So it's not like we have an operation after the return.
Okay, so it should be a tail recursive function, right? Is that, yeah, true, yeah. This is a tail recursive function. Why? The last thing that this function does for the recursive case is the recursive function call. Either this one or that one. We don't know which one, but either that one or that one, okay? So it's a tail recursive function, so this is efficient. This is as efficient as a iterative function. I mean, it could be as efficient as an iterative function. The compiler can do this minimization. Okay, good. So again, we are getting the best of both worlds: efficiency plus the provability of the recursive functions. Good. Okay. Usually, computer scientists. What kind of picture is that? Yeah, so you have been looking at that all along. Sometimes it's better, sometimes not. So there must be a problem with this. We should fix it. I don't know how. So I will let Osman Bey know this. Okay, so computer scientists, they are smart people. I mean, the correctness is okay. Correctness is our first priority. Write everything correct, right way. Write it object-oriented way, structural way, in a disciplined way. If it causes some efficiency problems, just find a solution. But don't try to give some compromises on your programming discipline or the object-orientedness of your code. Okay, so this is again, recursion has some problems in terms of efficiency, but we can solve it using these kind of solutions. Good. Okay, I think that was the end of the chapter binary search, and yeah. So this is how I check. No infinite recursion. Let's look at that one. No infinite recursion. Could there be an infinite recursion in this one? So what is the base case? Base case is either I find it or I couldn't find it. It looks like every time I take the middle element of these two, right? First and last over 2, okay? That's what I do. And my base case is first is greater than last. So by taking the middle element of these two, am I doing some kind of a mistake? It could be at most, if first and last are equal, right? So mid would be equal to first and last. That doesn't make first greater than last. So how do I reach this base case? This is what I'm doing, right? I take the first and last. If first and last are equal, it is, let's say it is 5 and 5. So mid becomes 5, and I will call my function first greater than last, no, right? So I wouldn't hit the base case. I would come here and first and last, again 5 again. So how do I reach the base case? Do I have an infinite recursion in this function? The answer is of course not. So how do I hit the base case? How does first become larger than last? If I keep doing this, taking the average of these two. If I make this, you know what I'm trying to do, right? Where is, yeah, okay. Is this okay?
But there is an odd number of elements.
This is not okay because if first and last are the same, and if first and last are the same, and that element is the one that I'm looking for, that's not good. So this is not good. Yeah. So how does this work?
Because isn't first and last our indexes?
What's that again?
Shouldn't it return mid number? Because
You mean this one?
no, yes, that one. Because isn't first and last our indexes? First index and last index, because we are using.
You are not answering my question, right? Are you answering my?
You said how should it work if first and last are the same number, right?
Well, if first and last are the same number, then then it should return mid. That's why I said that I cannot do that. But so it says that first should be, if first is larger than last, then I should return it. But this is the base case. How am I going to reach the base case if I keep doing this? If you take the average of two numbers, one of them will not be less than the other one, right? So how am I going to get first larger than last? Somebody gave me this at the beginning. What was our, they say that your first will be 0 and your last will be, let's say size, let's say it is 10. So I take the average, it's going to be 5. Let's say 0 and 5. I take the average is going to be 2. 0 and 2. I take the average is going to be 1. 0 and 1. I take the average is going to be 0. So it's going to be 0 and 0. It's not becoming smaller than the first one. You are not reading the code, just read the code. Next recursion call, it says that look for the number between first to mid minus 1. Okay? Okay, so it doesn't say first and mid, it says mid minus 1. Okay? So if my mid is 1, if first is 1, last is 1, right? If I make this 1, this is 1. If first is 1, last is 1, mid is going to be 1. So this is going to be 1 and this is going to be 0. Right? Just the opposite. This is going to be 1, this is going to be 2. So base case is okay. So no infinite recursion. So stopping cases perform correct action. Stopping cases, okay, I couldn't find it, return it. I found it, return it. Stop cases, and then what? And then recursive call. I have two recursive calls. This recursive call makes the problem smaller, but exactly the same problem. And whatever this one returns is my result. I don't do anything else. Okay, good. Any questions? I think that's it for this chapter. Let me start talking about the other chapter then, if there are no questions. Writing recursive functions takes lots of time. You need to learn how to write recursive functions. And usually there would be a good question in the final exam that asks you to write a recursive function. Okay, write recursive functions. How do you write recursive functions? Recursive functions, writing recursive functions, strings are best. Strings are best. Write strcat, strcopy, strncopy, strcmp. Right? Let's write the strcmp in our heads. What does strcmp do? It compares two strings, right? How does it work? Let's try to figure. Let's say, okay, this is my first string. This is my first string. I don't know the characters. And this is the second string. So let's think it recursively. I have these two. What is the base case? What would be the base case? Base. What again?
If one of the strings reaches the 0 now.
One of the base cases is that, yeah. But let's start from the easier ones. If this one is greater than that one, then I am done, right? If this one is greater than that one, return 1. If this one is greater than this one, then return -1. But if both of them are the same, then what do? I would say that I cut this part out. I cut this part out and call my function with the rest of the strings. Okay? So exactly the same thing, just the problem is becoming smaller. Okay? So far I did returning -1 and returning +1. How about 0? I mean, when should I return 0? 0 should be reached if both of them have the null character, right? If both of them have the null character, that means that they are equal, okay? So that's the 0. I think that's it. That's it, because at the end there is a null character here and null character there, right? So when I compare this one with this one, I will see which one is bigger. So I didn't write it, but I told you the main idea, because the recursive functions are written exactly the same. So what did I do? What are the base cases? And how is the recursion done? How do I make these recursive calls? So rest is just coding. You are very good at coding, and by doing these kind of examples, you will get better at writing recursive functions too. How about strncmp? strncmp. What does strncmp do? It compares first n characters, right? So I should check that number n every time. So I decrement it. So I will have another base case, right? I will have another base case. Good. Okay, so I will now go back to one chapter before and chapter 11. I will not talk about streams. I think TA will talk about it. I will talk about separate compilation and namespaces. Okay, separate compilation, you already did that with your C course, but let's go over it in a very quick way. And I know that you know how to write make files. TA showed you during the problem sessions make files. And let's see what the program says. Let's see what the book says about this. Okay, so we say that, okay, we like to keep our programs in separate files. We don't want to keep all of our programs in the same file. Why? Because we like to isolate different modules in different places so that I can compile them separately. Okay, so if I have a different file for each of my class definition, if I have a different file for each of my class definition, since I designed my classes in a reusable way, that means what? That means each class is sufficient by itself to be used by somebody else. So that means if I need to use that class, and I know that that class is implemented in a separate file, so I can just move that file anywhere I like, in any project that I like. So that's the beauty of it. If you put your classes, let's say, how many classes do we have written so far? Let's say I have my money class, and I have my let's say rational class. If I don't keep two of these in two different files, okay? If somebody needs money, then I have to send this rational too, right? That's not a good thing because he or she doesn't need the rational. So keep them separate. Money should have its own file. Rational should have its own implementation file. They should also have their header files too. In this case, this is a very nice self-sufficient reusable class within the interface, and the same thing for this one too. If I can use them in the same project, or I can just ignore this one or use only this one. Okay, so that's the idea of separate compilation, and we have been doing this a lot actually. But book has a separate chapter for this topic. Okay, the class independence is very important. Okay, if two classes are independent, they don't need each other, then they should be in different files. They should not be in the same file. Okay, that way I can reuse them in different places. If there is a problem with one of the files, if there is a problem with one of the classes, I can fix it independently of the other classes. Okay, this is the same idea as encapsulation actually. Encapsulation, what does the encapsulation say? It says that put the data and the functions that work on the data in the same capsule, right? And if we take this idea, make it more general, if two classes are related, okay, they need each other, maybe you can prefer putting them in the same file. But if they are independent, they don't need each other, don't put them in the same file, separate them, okay? That's the basic object-oriented principle, complete separation, okay? So these are the rules of the encapsulation. We said that before. Rules for separation, for encapsulation. All member variables should be private. That's what we said before. Unless we need them, there is a very good reason to make them public. All member variables should be private, okay? And basic class operations should be public member functions, friend or ordinary functions, overloaded operators, okay? These are how you should be visible from the outside world, okay? And this should make your interface. Your interface to the real world is your public member functions, okay, friend functions, and overloaded operators. And your implementation should be unavailable to the users of the classes or the customers. Rules of the encapsulation. If we use these rules of the encapsulation, then that means that we should separate our implementation from the class interface, also separate the implementation of the different classes between from each other. Okay, so let's see one example. But before doing that, maybe I should take 10 minutes of break. Okay, any questions before I take the break? Did everybody sign the attendance sheet? Did everybody sign it? Okay, 10 minutes.
type'ların null olabilmesiyle alakalı şey diyorlar ya, billion dollar problem diyor. Onlar
Type'ların null olması
şey, yani bir değerin null olabilmesi. Mesela onunla alakalı şey diyor. Bu null type'ını ilk oluşturan insan şey diyor. Billion dollar problem diyor. Hatta çok şeyleri oluyor. Şey hakkında ne düşünüyorsunuz? Bunu aslında yeni bazı diller deniyor.
Ben
Şey,
anlamadım type'ların null olması.
hani şey mesela null değeri direkt.
Evet ha.
Hani herhangi bir değerinin olmaması onunla alakalı. Şey deniyor da bazı diller. Hani mesela bir union tarzı bir variable. İnanları daha da genişletiyorlar mesela.
Evet.
Şey diyor. Ya değer olacak ya da hiç değer olmayacak. Ama
Evet.
bunu dil direkt enforce ediyor ki sen bunun içindeki değeri kullanmak istiyorsan diyor ya force'layacaksın, exception kaldıracaksın diyor.
Evet.
Ya da hani bir direnç oluşturmak zorundasın diyor. Mesela şeyde bunu denediler geçen. Bu exception'lar var
Ya
ya.
onu yaptığın zaman herhangi bir type, özellikle basic type'lara o kadar çok taviz veriyorsun ki o type ile alakalı şey açısından, yani yer açısından. Integer'se integer'sı, integer'ın bir null değeri olması, geçersiz bir değeri olması demek. Her bir integer birer kontrol etmen falan filan demek.
Ya onlar hakkında
Bir şey var.
şeyle ilgili bu şey yapmışlar.
Sadece okuda aklımda hiçbir şey yok ama. Sorsa aklıma işte gel. Çok derinler. Malzemeler çalışıyor. Hepsinin ayrı tadı. sorumluluk, projeli, işte sorumluluk. Hayır ya, devre dersinde business açılışları. Onu direkt şöyle gidiyor. Devre değil. Biz böyle zaten onu düzelttim. İlk baseline okudum. Altıncı okuyacağım. Benimki 3 slide oldu. Kafam bilmiyor ya. Anlıyorum ben hiç şey anlıyorum. Ben sözel ders çalışmayı bilmiyorum. Ben de ya. Böyle bir şey. Şimdi yazıyorum. Eşyanın kalitesi. Sonra foto çekeceğim. Gelirse yani olacak. Kopya çekebilirim galiba. Ben çektim yazdıklarımı. Yazdın mı bize? Yazdım. Her slide'ın sadece başlıkları falan. Evet evet, ben böyle bu kadar yazdım. Şey bazıları böyle koyu bookmarklamış. Bazıları böyle koyu işaretlemiş ya. O tanımlar falan. Onları sorardım. Saçma dediler falan. Kurumsal zor ya. Kurumsal da ben onu da aldım. Kurumsal da mı? Niye iki tane? Benim var diye. Yani bir de benim vardı. Çıksın vardı. Kurumsal zaten aynı zamanda. Bana imza atıyorlar. Girdim. Ama sınav oldu mu? Sınav olmayacak. Hafta sonu. Ha. Hiçbir derse girmedim. Sıfır. Başarılı. Zaten yüksek notla geçiyor musun? Bir şey yapmasan. Evet. Hiçbir şey yapmadan yüksek not aldım. Bundan ama geçersin. Geçeriz. Bu da şey kontenjan kalmamış. Kurumsal mı? Onu alacaktım ben. Kontenjan mı oldu? Olmaz ya. Direkt olmuştu.
O şey işte. Monopoli. Orada yapılıyor. Monopoli. İnternet monopoli. Bir de Türkçesini sormayacak. Tek türü var. Ama o tek türde diğer türlerin ortaya çıkmaması için
Böyle bir şey var. Monopolistik var. Monopolistik başka bir şey. Her yerde bulabileceğin şey. Sebze meyve tarzı şeyler.
kıyafet ayakkabı.
Monopolistik mi bu?
Perfect şey.
Perfect mi oynuyor?
Buğday, ceviz. O perfect. Monopolist. Kıyafet ayakkabı. Oligopoli, araba. Monopoli, dinozor.
Management.
İşletmeler. Yok, ders Türkçe ama sınav İngilizce. Ders hatta yarı İngilizce.
Niye? %5'iniz İngilizce, sonra derslerin başına İngilizce alırken
Ama şöyle yani, konuşurken hoca sürekli böyle. Şunu hangi hocam konuşurken sonuna gidiyorsun. Senin terimler İngilizce. Terim Türkçesi yok.
dersin başına gibi bir şey yok. İçine İngilizce yapıyorum. 5 dakika. Her zaman. Management functions. Management functions. 4 tane.
O neydi ya?
Az önce konuştuğumuz.
Düşünmeden önce koyduğum şey mi?
Organize ve kontrol. Boş boş dersler.
Doğru yanlış.
Test tutmamış. Doğru yanlış boş doldurma boş.
Kaç tane biliyorsun?
Bir tane boşluk doldurması var. Kaç tane doğru yanlış. Kaç tane de
Doğru.
her tür için 20 puan ise klasiklerin her biri 10 puan. Boşlukta doldurmaların her biri 4 puan. Doğru yanlışların her biri 4 puan. Ve testlerin her biri 4 puan.
Ama klasik bir tane sorarsanız. Soğuk falan sorarsın.
Strength, weakness, virtue,
Güçlü yanlarını yapacağım.
Bir tanesi de Sivas'taydı.
Şeyi sormuştum. Öğrencilerle sözlü Türkçe bilgisi var mı?
Bunlardan bir tanesi çalışmıyordu. Çalışıyormuş demek ki. Yani çalışır hale getirmişler. Onlardan bir tanesi çalışmıyordu.
Belki de çalışmıyordur. Belki de ben kullanmıyorum.
Nasıl kullanmıyor olabilirsin? Ne için kullanıyorsun onu?
Şu kameralar için.
Kameralar çalışmıyor mu?
Çalışıyor ama belki buradan alıyorum.
Yani onlardan bir tanesi çalışmıyordu.
Yok ya, çalışmıyor olmasa projektör çalışmaz.
Bence de. Yani yapmışlar.
Okay, so let's start the lecture. Am I recording? Show. What? Cancel. So these two has frozen. Okay, so we said that we are going to keep our interface separated from the implementation. Also, the same thing is valid between class implementations and the class interfaces. And let's see an example. The book has an example about a digital time class. Let me show you that one. No. For binary search book, the book gives you, I think this is available somewhere. See, I have all these words in the English dictionary, 87,000 words. So they are all sorted. Any word you can. Oh, so it is. So how many words that contains walk in it? See, these are so. That starts with the walk, walkable, walkings, etc. So if you are looking for a word, then you would do a binary search on this, and it would be very, very fast. If you need it, the book has it. So let me show you an example program, digital time. But before doing that, okay. Let me show you the header first. Okay. So this is my header for the digital time. We already know what these two are for. Do you know what these two are for? What do we call them? Header guards, right? Why do we need them? To prevent multiple includes. Yes. I mean, if I don't have them, if somebody includes my dtime.h 2 times, one after the other, right? In that case, what's going to happen? This digital time class will be defined more than once, and that will cause a compiler. The compiler will say that you have a class named digital time already. You are defining it second time. Okay, so I'm not going to talk much about this. The book has a good discussion, and you already know about it. So this is how we design our header files. Okay, at the beginning of our header files, I have this card. Okay, and I would say that I am using namespace std. This is my digital time. Digital time is something for represent the time. Okay, time of the day. I have the hour field. I have the minute field. No parameter constructor. Getters. I don't have the setters actually. Yeah, I don't have the setters. I have just the advance. Okay, just add this many minutes to the hour. Add this many hours and this many minutes. And I have a comparison operator, stream insertion, extraction operators. And these are all friends. Okay. These are all friends. So that's good. And I have hour and minute as my private, and I have read hour, read minute, and digit to end. I have three static void functions. They are in the private section. They are static because they don't need to reach the data. All the information that they need for this one, read hour, is at this parameter. What does it say? The hour has been set to the hour part of the time. I give the hour, integer hour, okay. Next input to be read from the keyboard is a time in notation, like this one. You understand what this does, right? I mean, it reads the hour part from the keyboard. This one reads the minute part from the keyboard, okay? So these two are reading from the keyboard. It reads hour and it sets the hour. It reads minute and it sets the minute. But they don't touch these two private data members. So they don't. Since they don't touch the data members, they are declared as static members. But they don't work. Actually, they don't work on the class itself in any way. So this place is not suitable for these three functions, especially for this one, digit to end. It takes a digit like 0 to 9 as a character, and it converts to a integer. Okay, so if I give this character 0 character, okay, it returns an integer 0. If I give a character 9, it just returns 9. So this one has nothing to do with this class. It has nothing to do with this. So I mean, I use the encapsulation principle to put these inside my class, but these aren't related to my data. Okay, these are like global functions, but I don't want to make them global. So we'll talk about them later. And this is my dtime.h, and this is how I implement those functions. Okay, so I would say that I am going to use this IO stream and C type. Remember C type from the C programming language? All the headers from the C programming language has to start with a C. So it used to be C type, now it is CC type. And I am using the standard library of the C programming language, so it is C is the stdlib. And I make the D time include, and I am doing this. My constructor error check, everything has to be between 0 and 24 and 0 and 59. Yeah, I set the day times, and if the hour is 24, I set it to 0, so it is the time would be from 0 to 23. Okay, and this is the no parameter constructor. Getters constant, nice. Advance works nicely. I just add the minute to the minute area, okay, and I get the modulo of this one. If it is larger than 60, then I get the modulo. If it is larger than 60, then I just edit. Okay, then I have the advance. The second one, hours edit and minutes edit. These are all regular stuff, okay? We did similar stuff with the money, I guess, right? So this is how you do the comparison. Okay, stream insertion extraction. Okay, see, this one says that if you are writing digital time to the screen, this is what you should do. Okay, the object hour, the object is this one, digital time. Since this is a friend function, it directly reaches the hour field. Okay, I print the hour and I put a column. Okay, and then I print if the minute part is less than 0, I put a 0 at the beginning, less than 10. You know what I am trying to do here. It's just I am trying to say if it is if the hour is 9, it is 9. If it is 5 past 9, then I should do this. I shouldn't do this, right? I mean, you don't want to say this, right? It's not good. It should be this one. So that's what it is doing, and that's it. You understand what this one does. This is the static function, remember? This is a static function that converts a character to a digit. And this is the read minute. It just reads 2 characters from the keyboard. If they are not digits, okay, they should be both digits, then I terminate my program. Otherwise, this is what I do, okay? Convert each one to integer digits, multiply it with 10 plus this one. Now I get the minute part. It should be between 0 and 59. Okay, so this read minute, as you see, it should not belong to this class because it doesn't use any data from the class. It doesn't refer to any class elements. And it doesn't obey the encapsulation rules, but I don't want to make it global either. So I put it as a static in there. It's a static, so it will not change anything, or it will not reach any private data or any data. But I should find a solution for this one, or I should find a solution for this one too. And the same thing for the read hour. Okay, read hour is a little bit more complicated than read minute, but I will not talk about that. The standard logic. Okay, good. So I have D times CPP, D times H. So how do I use them? I use it this way. I say that I have a D times H IO stream. I have 2 digital time objects, and I use the assignment, of course, no problem. I can use the advance. I can compare them. So my customer code is this much. My customer needs to see this header file. That's only what the customer sees. And the implementation is hidden. So I have 3 files now. The driver code, timedemo.cpp, that includes the main function. I have my header file, dtime.h, and I have dtime.cpp. Okay, so that's the whole thing. This is how we should do our development. Let me go back to beginning of the chapter and and I would say that, let's say we have a large project, okay? We have a large project, and we said that we need lots of classes. Let's say I have class A, class B, class D, class E, class F, and class G. So there are lots of classes. They have to be implemented. They have to be implemented and tested. We say that this is too much work. Let's get 3 developers: developer number 1, developer number 2, and developer number 3. Let's have these 3 developers working on these classes. So I will assign this developer 1 the class A and class B, and developer 2 is class D and E, developer 3 class F and G. Okay, so these 3 developers are working on their classes. They are working on their CPP files and the header files. Okay, and when they are done, I can compile all of them together. How many CPP files do I have? 1, 2, 3, 4, 5, 6, and there should be a file that includes the main. Total of 7 files. Okay, total of 7 CPP files. But each CPP file has a header. Okay, and I have total of 6 header files. I have total of 13 files. 7 of them are CPP files and 6 of them are header files. Okay, so when I make this compilation, 13 files are included. 13 files are included. Okay, usually before these developers start working on their files, everybody writes their own header file. Okay, before making an implementation, and you write your test file. Okay, this one that includes all the header files, and writes a test file, a test main function, just to see everything is compilable. See this one? In order to able to write this file, I don't need to have this time.cpp. I don't need the implementation. All I need is dtime.h. Okay, it is here. I have written this before. Okay, I am just including it, and I am compiling my time.demo.cpp. I can compile it without the dtime.cpp file, right? So that's what I'm doing. So this is what I would have done. How many files I have? I have dtime.h, dtime.cpp, and what? And time.demo.cpp. time.demo.cpp. In order to compile this one, I don't need to see this header file. Okay, I would just compile this one without linking. This will include dtime.h, and I will get a what? I will get a time.demo.o object file, right? This is what I get. And then if I compile this one, I will get dtime.o, another object file. If I link these together, okay, I will get my executable code. But to be able to make this compilation, I don't need to see this .o file. Okay, so what I am trying to say is that first design your class, keep the interface separate from the implementation. Try to use that class in the driver code just to see if the customers are okay, if everything that you want to do is possible. If it is possible, then that means that your header file is okay, your interface is okay. Now you can start implementing your dtime.cpp. Okay, so implementation comes later. So if I apply the same idea here, okay, these 3 developers, they come together, they design their header files, all 6 of them, and somebody writes the test.cpp, just to use all 6 of them inside this test.cpp. If everything is fine, if test.cpp is compilable, and it seems it is okay, then everybody can go back and everybody can implement their CPP files. Okay, so designing classes is different than implementing your functions. Implementation is of course important, but designing is more important. And this kind of structure makes it easier to separate this designing process from the implementation process. Okay? So if I didn't do that, if I let each developer develop their header files and CPP files independently, after a month they worked on these files. If I try to write my test.cpp, if I realize that there is a design error, my code is not compilable, I cannot do some of the things that I like to do. That means that some of these developers will have to make lots of implementation changes, which was not unnecessary, which was not necessary, because they could have realized this at the beginning of the project. Okay, so these are the nice things about separating your interface from the implementation and keeping your implementation hidden from the customer, the end user. If I know that there is a problem with the class A, I know who to go to, developer number 1. Okay, if there is an implementation problem, he will fix it. If I know that there is a problem with this one and this one and this one, all three of them are fixing their own problems in parallel, right? So everybody has their own responsibility, and each one is trying to be a reusable pieces of software. And this is how the object orientation with the C++ works. Okay, good. Any questions so far? So maybe I didn't say anything new with this one, but this is what the book discusses. Separate compilation. I think there should be a thing that I need to talk about. Compilation unit. Okay. The definition of the compilation unit is important. Okay. Let's go back to our original D-time stuff. Okay. To be able to get this executable, okay, created, I need two compilation units. One compilation unit is this one. The other one is this one. Okay. I need to run my G++ compiler 2 times. One is for this one, and one is for this one. So I have two compilation units. Inside that compilation unit, I have the time demo.cpp, all the code. Also, I have the dtime.h header file too inside this compilation unit. And inside this compilation unit, I have dtime cpp implementation files. Also, I have dtime.h, because dtime.h is included by both dtime cpp and time demo cpp. Okay, two compilation units, and they have common code. Okay, so that means that if I change something inside this header, I have to compile both this one and this one. Why? Because these compilation units are sharing this piece of code, right? So changing something in the header is important. If you change something in the header, there are many files including that header, so you need to compile all of those files again. With this example, okay, if you change this header, whoever included that header, I don't know, this one included it, maybe this one too, okay? All of those files has to be compiled again. So we need to be very careful about changing our headers. Headers are important. If you make a change in the implementation, nobody cares, because nobody other than this implementation uses this implementation. I didn't make any promises to anybody, okay? To anybody. So this definition of compilation unit will come again, and we will use it when we discuss the namespaces. Good, compilation unit, I talked about it, and I talked about guarding against multiple inclusions. Guarding against multiple inclusions, that's fine too. Okay, we talked about it. Multiple compiles of the header file. Guarding, we talked about it. And I think these are all things that you know. So the second part of the chapter is the namespaces. If you don't have any questions about the separate compilation, I will talk about the namespaces. We have been delaying the discussion about namespaces so far. Namespaces, we will define it, okay? And namespaces are actually a continuation of this encapsulation principle. Remember encapsulation, we said that all the related data and the functions that work on the data are encapsulated in the same structure, same class. That's what we said. Namespaces says that we can extend this idea. All the classes that are related to each other should be put in the same place. Okay? Let's say I have three classes, class A, class B, and class D. Okay? These are related classes. Let's put these three classes in the same namespace. So namespace definition is this. Okay? A collection of name definitions. This is how you define a namespace. I say namespace GTU name. This is like STD is a namespace. Remember STD? STD is a namespace. I can make my own namespace too. I have my own namespace, GTU namespace, okay? Inside this GPU namespace, GTU namespace, I have class A, I have class string, okay? And I have a global variable. I don't like it, but I have a global variable. So these three name definitions, okay? These three name definitions belong to this namespace, okay? So it's kind of an encapsulation principle application. Whenever I need to use this class A or class string or this global variable, I need to say that these are from this namespace. Okay, these are from this namespace. You might say that, how come you can have a class name string while we have a class name string inside our STD? That could happen. See, inside the namespace STD, I have my vector class, I have my string class, I have my global objects, cout, cerr, and cin. Okay, these are all defined inside my STD namespace. Somebody has defined it, and I have been using them. Okay, these are collection of names inside the STD. I make a decision. I am saying that I have a new namespace. It's called GTU name. Okay, I have my own classes, class A, global variable and files, and a class name string. It could happen. This one belongs to this namespace, and this one belongs to this namespace. And they can work. They can be used in the same program. My class string and this STD class string are two different things. Okay. So namespaces are good ways of organizing your classes and your name definitions. Okay. I don't like global variables, but if I like to use it, yeah, I am using it in here. I didn't like global variables, but as you see, cout, cerr, and cin, they are all global variables. They are global variables, and they are defined inside STD, namespace STD. Okay, so programs use many classes, many functions. Some of them are related. You put the related ones under the same namespace. Okay, so anybody wants to use your classes that they bought from you, then they need to use your namespace, like we have been using with the STD namespace. Okay, STD was designed before, and STD, I am using STD by using at the beginning of the using namespace STD. I am using all of them. Okay, good. We already did that before using namespace STD. Makes all definitions in STD namespace available. Okay. Sometimes you may not want to do this because see, inside namespace STD, I have the string, right? And after that, maybe before this, if I do using namespace GTU name, if I do these together, and if I say that now I will have a string st Compiler will get confused. Why? Because there is a string class available inside this namespace. There is another string class available inside this namespace, okay, std. So which one I'm going to use, okay? So sometimes you may not want to do this. Sometimes you would say that instead of writing these, sometimes you would say that I need a standard namespace string like that. Or I need a GTU name string. Okay, fully qualified name. Sometimes I do this kind of stuff, and we will see how that happens. Okay, good. Any questions? Yes.
Back in the slide, this I saw that can be turned on and off.
Sure. Yeah.
We do that.
Well, we will see examples of it. We will see examples of it. Maybe I should show you it right now since you asked it. There was a, yeah. Between these two braces, I am using namespace NS1. And between these two, I am using NS2. Turn on, turn off. Turn on, turn off. Okay?
It's like variable, it has a scope.
What's that?
It's like variable, it has a scope.
Yeah, sure, yeah. It has scope. So this namespace, using namespace directive is available from this position to this position. This one is available from this position to this position. And it looks like inside NS1 and NS2, both of them has this function, my function. So there are two functions with the exact same, this is not overloading, okay? Exactly the same signature, same function, name, available, but two different functions. Okay, how can I do it? So what kind of a design decision that you have a same function name for two different functions? Isn't that a bad thing? Why do I have a two different functions with the same name and same signature? That's a bad thing, right? That's an error. Why are we allowing it?
Maybe two different people wrote it down.
Yeah, I bought two different libraries from two different companies, and by coincidence, both of them have this function, my function, right? Humans are not that creative when it comes to naming the functions. They all use the same function name, okay? They are very similar, okay? Like the print values, read values, calculate stuff, right? They are very similar. So they may end up, if they write thousands of functions, they may end up writing the same function name with the same signature, okay? Like I like to have my own string in my GTU namespace, but the standard library has a string too. So why should I call it string GTU? I just call it my whatever I like to call it, okay? So this happens a lot. That's why we have the namespaces to get rid of these kind of confusions. Okay. When I use that class string, I should know where it is coming from. It is a standard string or the my GTU string. Okay. That makes it easy to debug too. Okay. And we looked at this using directive. We have been using it. Okay. Sometimes this is not preferable, and we are going to see how to deal with those. Okay, we used the namespace std before, and namespace std contains all the names defined in many standard library files, okay, including the vector, including the, for example, if I look at this, if I find string.h, if you look at the string.h, at the beginning of the string.h, it says I am defining this class as part of namespace std. Okay, this is string.h. In vector.h, I have this. I am defining this std. I am defining this vector as part of name std. Inside I have string.h, I would say I am defining this class inside this namespace std. By the way, there is a allstream cout object in there too. Okay, so if you include this one, or this one, or this one, you are getting the definitions of all those namespaces. Okay, good. Before going further, maybe I should show you a namespace definition, chapter number 11, right? What happened to those? Okay, let me open it. So where is my, oh no, I couldn't find it. Okay, let's go to the book then. Book, from the book, daytime age, namespaces, okay, good. Okay, let's see this example. Let me erase these. Oh, does it work? Can I erase them with my... Okay, I have this file, okay, just to demonstrate it. I have one namespace space 1, I have another one space 2, okay, both of them define the same function, and I do this. Using namespace space 2, this one calls this one, right? And this one calls this one, okay? And then when I say big greeting, this one calls this one. This is like a global function, okay? Of course, it's a global function. When I say big greeting, it calls this one. Question: If I take this line 23 and put it inside this braces between these two, which one? What would I get? Would I get a compiler error? No, of course not. Why? Because I said I have namespace space 2. No, I mean, using this namespace space 2 doesn't shadow this global function. It is already there. So global function can be called anywhere that you like. How about this one? Just erase line number 18 and line number 19. Delete line number 18 and line number 19. Compile this code. What happens? Line number 21 will produce an error message, right? Line number 17 will be fine, but line number 21, it is not line number 20, okay? It is line number 21 will give you an error message, because using namespace space 1 doesn't cause this confusion between two gradings. This one causes it, okay? So it is okay to use these two spaces at the same time, as long as you don't make a confusing function caller use a class. Okay, so this is a good example. And by the way, this is how you define the function inside the space 1, and this is how you define it inside space 2. Okay, good. So that was one example from the book. There are some other examples from the book, and let me show you those. Those are good, nice examples. Remember our digital time class, our header, okay? And inside my header, all of the class definitions and everything is done. Now I have my namespace, D times Savage. The author of this book has chosen this namespace, name, D times Savage. And this is my implementation, this is my class definition. And this is my header file. And this is the D times CPP. D times CPP says that I am including D time H, and I will do this, okay? I am making this implementation, okay? Now after that, I will show you how to oh, this is the whole thing, okay? This is my This is my implement. This is my class definition. Yeah, good. 11.8. This is already, we have seen, this is the full code. Okay, this is my header file, the digital time age, right? And this is my, I am trying to show you okay. My main function is implemented in timedemo.cpp, okay? Inside timedemo.cpp, I say that my digital time belongs to this namespace, d time savage, and d time savage, and whenever I say digital time, you should use it from this namespace. So instead of using directive, I am using the other version of using a name from a namespace. Okay, this is another way of using stuff from the namespaces. I think I have a nice slide about. Okay, I did that already. Okay, this is called using declaration. When you say using namespace fun1 and using namespace fun2, fun1 refers to from now on namespace fun1, and fun2 refers to namespace to fun2. Okay, so this is called using declaration. Okay, so I have using definitions and using declarations. There are three ways that I use this keyword using or the namespaces. Either I would say using std string, using declaration, or using directive, using namespace std, or directly fully qualified name std cout. Okay. So far we have been using this one, right? From the beginning of the semester, we have been using this one, and sometimes I have used this, right? Did we use this one before? Using std string, using declaration. I might have, I don't remember, but this one is possible too. So usually for the string, for the standard library, we use this. Okay. For the standard library, whatever it has, everybody knows it. But for the others, usually we try to use either this one or that one. This one or that one, because you don't want to make everything available. That might cause some confusion between the names inside this std and the names inside those libraries. Okay, good. Choosing a good name for namespace is important. Okay, if everybody chooses this name, my namespace, that's not a good thing. If everybody says that if everybody chooses this name, everybody's namespace would be the same name. That's not a good thing, right? That's not a good thing. So usually people use their last names or their organization names or their class names, like the G2, CSE241, etc. Okay, so if I developed a library from this class, from this lecture, maybe this is a good namespace name, but this is not a good namespace name. Okay, that would be just against the whole idea of the namespaces. Okay, this is I already showed you, and I think I skipped some stuff. I don't have time to fully talk about them, but maybe I should not. Yeah. Global namespace is a namespace that is always available. Okay. We have been defining our namespace, our classes and our functions for this namespace. Okay. There is a global namespace which is always available. If you don't specify any namespaces while you are writing your classes or your functions, then you are writing them to your global namespace. Okay, it is always available. All code goes in some namespace. Whatever you do, doesn't matter. Even if you don't specify them. If you don't specify them, your code goes into global namespace. To be able to use the global namespace, you don't need to say anything. Okay, there is no using directive or using declaration or any other way to use a global namespace objects. Okay, global namespace is always available, and it is implied using automatic using directive. Okay, so that means that in C++, you cannot live outside of namespaces. You cannot say that I am not using any namespace. If you don't use any namespace, you are in the global namespace. Okay. To be able to use names from the global namespace, you don't have to do anything. You just call them. You just use them. So far we have been using this global namespace without realizing it. Okay. Without realizing it. So that's one definition. Good. And I think we talked about this, multiple names and how we handle that. And this one, I already looked at it. Using directive has block scope. I already did that. And creating a namespace is as simple as saying, I have this namespace now, and I am putting my code in there. Okay. And what else? There is a. So why do they have these two things separated? Because this one usually belongs to the header. This one usually belongs to the implementation. You understand it, right? I mean, let's try to compare a class definition and namespace definition. When you make a class definition, it is very similar, right? When you make a class definition, you say that class, my class, and you put all of your data, all of your functions, and you just end it, right? That's it. All the class members have to be defined between these two braces. For the namespaces, yeah, it starts the same. Instead of saying class, I would say namespace, and name of the namespace. I put it in there. Inside the namespace, I can do lots of things like the class definition, global function definitions, or the global variable definitions, struct definition, whatever you want. Okay, but whenever you're done with the definition of the namespace, that doesn't mean that you cannot add any other thing to this namespace. In another file, you could say that I will continue my addition to this namespace space 1. So you can separate your namespace definition into more than one file. Okay, like with remember how I showed you? Yeah. So the definition of namespace std is divided into many different files. It is divided inside this header, inside this header, inside this header, or inside the implementation files too, string.cpp, vector.cpp. Okay, so it is true that definition of a namespace is similar to class definition, but the difference is I can separate my namespace definition into more than one file, even in the same file, into more than one position. Okay, so namespaces, they are simple. They are just extension of idea of encapsulation. What is encapsulation? Putting all the data, related data, also the functions that work on the data in the namespace, name capsule, and namespaces make this idea even more generalized. It says that put all the related name definition inside the same structure, which we call namespaces. That would make our life a lot easier. Okay, any questions? I have one important concept that I didn't talk about today. It is called unnamed namespace. We'll talk about it and on Friday. And after that, I think I will be done with this namespaces chapter, and we can start talking about inheritance, which is the, remember, abstraction, okay, is important for an object-oriented programming language. Encapsulation is very important, Okay, inheritance is important too. Inheritance is another basic principle, basic pillars of the object-oriented programming languages. We will talk about the inheritance, and depending on the inheritance, there is this concept of polymorphism, and those three things will be the last two most important things about the object-oriented programming languages. So on Friday, before coming to class, maybe you should read the book about the inheritance. Okay, so I'll see you on Friday.